Hi, I'm Pascal Lauer and I will be presenting Max Fickert and my work which improves LM-cut by introducing a quicker cutting algorithm and some way of practical type breaking for the precondition choice function. To put it into one sentence what LM-cut is, I wrote down the following. LM-cut is a heuristic that computes admissible estimates of the perfect delete relaxation heuristic by iteratively computing disjunctive action landmarks. To do so, it constructs something that is called a justification graph. And I will do an example how this is constructed now. This example is a visit all task, so there's a player in a grid and he wants to visit all tiles. We will now encode this as a strips task, so we have add facts for each position 0, 0, 1, 0, 0, 1 and 1, 1 to say that the player is at the current location. Of course, we want some way to remember that the player has been at a certain tile already, so we also have facts called visited. The player needs to be able to walk around the field, so we have an action that is called walk, and our set of actions will be just those actions that move between adjacent tiles. Initially, the player is in the bottom left corner, and our goal is to visit all tiles. Before we construct our graph, I want to start with an hmax computation. We set the cost of our initial state to 0 and then apply all applicable actions. So the cost of add 0, 1, add 1, 0 and the respective visited facts is 1. We again apply all applicable actions and now our facts are reached, our goal is fulfilled, and we know that add 1, 1 and visited 1, 1 cost 2. Now we want to construct the justification graph, and as nodes we choose all facts in the task. And we also introduce two new nodes, I and G. And now we build edges for each action. For each action we choose the maximal costing precondition judged by the hmax cost and connect it with the whole add list of the action. For our walk action this is really easy because we have only one precondition, so it has to have maximal cost. And then we can just connect it with the add list. If we do this, this looks something like this. And you may have noticed that there's also one action outgoing from I that we have not defined before. This action is basically coming in with our new node and just says that the precondition is I and we can reach, so the add list is visited 0 and add 0, 0. There is also one action coming with G, which has the same intuition. Instead of coming from I to our initial state, we now want to reach G when the goal is fulfilled. So our precondition is the goal and the effect is G. So now we also want to construct the edge for this action, and we can choose between these four facts. But visited 1 is the node with the maximal hmax cost for these four facts, so we will just choose it. I won't be able to compute the LM-cut value of this graph within the time limit, so I will just shrink it down a little bit. I will merge these nodes and only consider the forward moving actions. And then the graph looks something like this. We will now want to determine the zero cost goal zone and the before goal zone. The zero cost goal zone are just those facts from which we can reach G via only zero cost actions. And the before goal zone is every fact we can reach from I without passing through the zero cost goal zone. The cut then is identified by those actions that reach from before goal zone to the zero cost goal zone. So these two actions. And we will determine the minimal cost of all actions in the cut and remember it. Now we reduce the cost by this remembered cost, the cost of each action by this remembered cost, so we end up with two actions here with cost 0 and we will recompute hmax. And this ends up with all these facts costing just 1. And we again want to determine which precondition we choose to be the starting point of our edge. And now we can choose any one of these three, because all have the same cost, but we need to choose only one. So I will just arbitrarily choose add 1, 1. And when I do this, the zero cost goes on, becomes this upper part. This is our before goes on, so the cut looks like this. And we are done because the stopping condition is when there is a path from I to G, which consists only of zero cost actions, which is the case here. So we can compute lm_cut by adding up all the costs of our cuts. And this is 1 plus 1 and results in 2. The first enhancement we propose is focusing on the cutting technique. As you have previously seen, this has currently been done by determining what the zero cost goes on and the before goes on is. And I will just show you an example how this works. The zero cost zone is determined by starting with G, then exploring all zero cost nodes backwards, for example this zero cost node. Then we also get at 1, 1, we can't explore zero cost nodes, zero cost edges anymore, so we will stop exploring. The before go zone starts at I and explores all nodes that are not in the zero cost zone and connected to our current before go zone. So we can explore at 1, 0 and at 0, 1, and then we are finished because we can't find nodes anymore that are not in the zero cost zone. Then our cut was determined from the before go zone to the zero cost zone. The modification now will be to just ignore our before go zone. We will determine the cut by all those actions that point in our zero cost zone. When we do this, for this example, this will be the same cut. But I can also show you an example where this overestimates the cut. So here we will determine this action and this action in the cut. But with our before go zone technique, this would only cut this action. But in this example, the heuristic value would actually not differ. And the expectation is that such cases do not occur often. The motivation, however, why you would want to do something like this can be really nicely seen here. So in first iterations, your zero cost go zone will be really small, whereas the before go zone is really big. So when you just need to explore the zero cost go zone, you save the time you would need to spend to explore all of this justification graph parts. And this will end up in a huge speedup. The second enhancement focuses on type breaking when we have multiple preconditions that have the same hmax cost as we have previously seen. So we will just revisit our example where we already had cut once for the cost of 1, and now we had to choose between f1, f2 and f3, which had the same cost, and we have previously chosen f2. Let's just choose f1 and see what happens. If we do this, our zero cost zone looks like this, our cut is this, and we will just recompute the cut, recompute hmax. Now we can choose between f2 and f3, we just chose f3. Then we again determine the zero cost zone, compute the cut, and now we have a path from I to G, which is only consisting of zero cost edges, and we are done with the computation. But now our lm_cut value is actually 3, whereas before, when you recall this example, we have ended up with an lm_cut value of 2. So indeed it matters which precondition we choose, but how do we determine automatically which precondition is more attractive to choose? Well, intuitively speaking, my idea was that when we cut fewer actions, we will probably result in a higher heuristic value. And how do we cut fewer actions? Well, if our zero cost goes on, stays smaller, there are less actions pointing into it. Also, this does not generalize, but intuitively, most of the time this should be true. So the idea is to keep the zero cost goes on small. One criterion that we introduced was called border detection, which just means that we want to select a precondition when we do not expand the goal zone further with it, when it finds a border of the goal zone. And in this case, this would be f3, because here we do not expand the goal zone further from f3, but with f2 and f1 there are zero cost actions, so we would further expand it. The motivation behind this is that if you have such a structure where there are multiple zero cost actions going out, and this repeats over several nodes, In this case, you would just have an exponential blow up with respect to the level. You will have this recurring structure. And here, this is not exponential, but it will still reverse, right? You still keep on expanding the goal zone, and you're again and again adding more actions to it. Even if when you expand this node at this moment, you add more actions into the cut. So, but what if we can select such a node if there are just zero cost actions coming in? We had multiple suggestions for this in the paper, but I will skip this due to time constraints. I will just introduce one more criterion, which says if a precondition is already in the goal zone, just select this precondition. And this seems kind of counterintuitive, because what I said before is we construct a justification graph, and afterwards we want to expand the goal zone. And if we do this, we can build a justification graph based on information of the goal zone. But what happens in the code is actually a little bit different, because during the expansion of the goal zone, we just decide how the justification graph is built. So let's start expanding our goal zone. When we do this, we start by adding g, as I have previously explained, and now we want to expand this zero cost edge. When we do this, we would just now find out that the according precondition for this is F3. So we will just select F3, and the same for F1. Now it's interesting that this is just selecting preconditions on the fly, because now we can decide whether we want to choose F2 or F3. And since F3 is already in the goal zone, we will choose it. Since we have a precondition that is in the goal zone, when we expand our edge, the goal zone will not grow. If we would have chosen F2, F2 would have been also in the goal zone, and we would have cut this action, whereas with our choice of F3, we did not. So let's have a look at the results. The results of quick cutting just show what we want. When you have a look at the expansions and the initial heuristic value, you see that they stay roughly the same. So this should mean that we don't really lose information with our overestimation. But if you look at the evaluations per second, you can see that they are a lot more. So we really gain the speed up, but don't lose information, which is exactly what we wanted. So let's have a look at the type breaking results. Arbitrary stands for the initial configuration, so without any type breaking. GZD and BD for the two techniques I've shown you before, and goal zone detection plus border detection basically means we try to apply goal zone detection. If it does not work, try border detection. So in park printer and parking, we can see that there's a smaller coverage increase. With respect to our best configurations, we gain 3 and 4 coverage respectively, but visit all and free sale are really our prime examples. In visit all we increase for 20 coverage, and in free sale for 18 coverage, which is quite a lot. And also overall you can see that the coverage just increases by a high margin. So the question is, if we have these examples of where the type breaking works really well, are there also examples where the type breaking does decrease the quality of the heuristic? And so we want to compare the expansions of our best configuration with the original type breaking. And as you can see, except these outliers, the expansions are generally smaller or roughly equal. So I guess you can really say that the heuristic has improved in general. To conclude my talk, the first point I want to make is that we can see that we can still improve the performance of LM-cut with extensions. There's nothing new per se. There are already papers out there, for example one that computes landmarks incrementally and so recycles landmarks that were already computed before, and so saves time, and therefore LM-cut runs faster. But what we did here is to improve the value, and the most significant part was this type breaking. And the rules that we introduced are really basic. So the motivation would be to come up with a more sophisticated way of type breaking. and therefore improving the heuristic even more. Thank you for your attention.